we are going to not directly study this equation yet. We are going to study a limiting case. That is when u is equal to 0. So we don't have any advection. It is like the case when, let's close all. It is the case when we have a 0 u and some kappa, let's say 0.01, where we draw an initial condition like that, and we see the solution slowly dissipates. It doesn't move towards one direction or another, but it slowly goes from a weakly solution into a smooth solution and slowly smoothes out to some constant. So that's the behavior of a heat equation. That's we call a parabolic equation. We are going to show you what it means a little bit later. So this models the evolution of temperature, let's say in a solid bar. So initially, if you make the temperature distribution to be non-uniform through the dissipation through heat conduction, the temperature is going to become uniform after a while, right? Okay, so in u equal to 0, the differential equation becomes partial u partial t is equal to kappa times partial square u partial x square. All right, and we know pretty much the behavior of the differential equation, smooth things out. And okay, so first of all, let me discuss why it is called a parabolic equation. Okay, what it means by a parabolic equation. A parabolic equation, at this point, I'm going to introduce the meaning of parabolic maybe sometime later in this course. But now, let's just look at a space-time diagram. And for a parabolic equation, what characterizes parabolic equation is what I call the domain of influence. The domain of influence means if at time equal to 0, if you change the solution on one point, so let's say you have, let me go back to MATLAB. If you change the solution to one point, which means, which can be seen as if you make the solution equal to 0 except for one point, it's almost a delta function. Okay. As time goes on, how does that solution affect the solution at different space and time points? In this, we are going to see that the solution diffuses, which means after even a slightly later time, the solution at this point is going to affect a wide area of solutions. So the domain of influence is essentially the whole domain after the time of perturbation. This is different from other equations like hyperbolic equations, which corresponds to the other limiting case where kappa is equal to 0, but u is not equal to 0. So if you have the previous case where kappa is equal to 0, you see if you make any perturbations, the perturbation is not going to diffuse. It is not going to affect neighboring solutions. It is just going to slide through the spatial domain at a particular speed. So you are only affecting a narrow range of spatial domain by this perturbation, as opposed to the parabolic equation where if you put one perturbation, it will affect a wide area. Actually, mathematically, it affects the infinite domain instantaneously. Oh, question?
Is the effect instantaneous or does it take time? Like the way you see it?
Very good question. So for parabolic equation, the effect is instantaneous. The time makes the effect of the perturbation more and more at faraway points. But for the perturbation to have non-zero effect at another spatial point, the effect is instantaneous. That is hard to see with naked eye, but like through some mathematical analysis, you're going to see the effect is instantaneous. And if you go to Stadler and look at the reading materials, you can read more about the distinction between parabolic, elliptic, and hyperbolic equations. Highly encouraged to do that. Okay, now we have seen that in a partial differential equation, the solution, even at a particular time, is not a few numbers. It is a continuous function. Right? When we plot the solution, it is a function of x even at a particular time. And in a computer, it is in some sense impossible to represent arbitrary functions, because a function in some sense is an infinite dimensional object. So we have to approximate the function through discretization. And I'm going to tell you a little bit like right now, like the different ways of discretizing a function. So here I'm just going to introduce finite difference and finite volume discretizations, and for you to see like just two different ways to discretize a function. So I'm going to have a finite difference demo running here. And I'll ask again somebody to come up and draw a continuous function. And we're going to watch how the finite difference method is going to represent that function in a computer. Please. Left to right, please.
Sure.
All right. Good. So what's your name?
Andrew.
Andrew. Okay, so Andrew drew a continuous function, right? It's not exactly smooth, but it is continuous. And in a finite difference discretization, the computer has forgot practically what you have drawn, except for these red circles. A finite difference discretization basically keeps only the value of your function at particular points in the spatial domain. These are what we call the grid points. A finite difference discretization only stores the value of the function at the grid points. If you have 11 grid points in this case, finite difference method stores the function as 11 real numbers. So that's how finite difference stores a function. This is as opposed to a finite volume, which is the second method of discretization we are going to talk about. So can somebody come up and draw me another function, and we are going to see how finite volume is going to discretize this function. Just to get a different feeling of how different methods discretize these functions. Could you please? Sure. All right, good. So this is finite volume. And as we can see, the computer in this case does not store the value of your function. What's your name? Todd. It doesn't store the value of Todd's function at the grid points. Actually, it doesn't store the value of the function anywhere. Instead, what does it store? Yeah, the average of the function within, in between each grid points. These are in finite volume are called control volumes. This is why it's called finite volume, because these intervals within each we average this function is called the volumes, or the control volumes. So this is an important distinction between finite difference and finite volume. Finite difference, I just know the value of the function at particular points instead of knowing the average of the function or something else about the function. Question?
Will you be also studying higher order approximations in this class, or is it first order?
We are going to. So the question is, are we going to study high order discretizations? Yes. And we are going to study high order discretizations in both finite difference and finite element. So, and in this, I'm going to explain a little bit about what is high order. Can you tell me what is high order?
When I double my number of points with which I approximate my solution, the quality of my solution increases by the power of 2. So if I am first order, then my quality of solution is 2 times better. If I am second order, my quality of solution is 4 times better.
Okay, good. So the question, so your answer is, when I double my grid points, how much does the quality of my solution gets better? Is the approximation error, is the error in my solution gets shrunk by half or shrunk by more than half? It's good. So that answer means your definition of high order is greater than first order. And we're going to study primarily first and second order methods. And we're going to study a little bit on methods that are higher actually than second order. And if you talk to like aerospace engineering people, a lot of people think of high order as higher than second order, which means third order, fourth order, etc. Right? So, but different fields have different meaning of what is high order. Okay, good. And and by the way, high order methods does not depend on how you discretize the function. A high order finite volume method still discretizes function as the volume averages. A high order finite difference method still discretizes the function as the value of the function at the grid points. All right, that has nothing to do with high order or not. All right. So let's